95% of them. Complete waste. Just expensive space heaters.
Here's a shocking truth. Something outrageous. Something you will probably disagree with. 95% of MCP servers are completely or mostly useless. They're slower, more complex versions of tools that already work perfectly. But here's the twist. I'm not an MCP hater. I'm not saying that MCPs are bad. In fact, I believe MCPs are what we need to make AI agents truly powerful. So, what separates the game-changing MCPs from the time-wasting ones? And how do we build MCPs that actually matter? By the end of this video, you will know exactly which MCPs to avoid, which ones to build, and the architecture patterns that make the difference between revolutionary and redundant MCPs. Here's how we'll get there. First, I will explain what MCP actually is using a simple analogy that will make everything click. Then I will show you real examples of MCPs that are complete wastes of time and prove my 95% claim. Finally, I will reveal or explain the architecture patterns and design principles that make the remaining 5% so powerful that they transform how AI agents work. We'll take a quick break for me to introduce you to Outskill, the sponsor of this video. Here it goes. A significant percentage of companies are already using AI, and many are laying off people because of it. People fear AI will take their jobs this year. Now, that probably sounds scary, but here's what's not obvious. They're also hiring. They're hiring people who understand AI, who can use it, who can build it. And this isn't just about jobs. If you run a business, freelance, or are building something of your own, AI is not optional anymore. It's leverage. The ones who learn AI will now outrun those who don't. So if you want to stay ahead, hire better, build faster, start learning AI today. And that's where Outskill comes in. They have a 2-day AI mastermind happening this weekend on Saturday and Sunday. 2 days with expert mentors. 16 hours of learning, 10 plus AI tools. You go from an AI rookie to an AI pro and stay relevant. Now, here's the important part. This training normally costs $895, but Outskill is giving away 1,000, and I repeat, 1,000 free seats to my viewers of this channel for the next 72 hours. The link is in the description over there. Check it out. Alternatively, join the WhatsApp group for more information. And now let's go back to the main subject. Let me ask you a question. How do we humans accomplish the complex tasks we perform every day? How do we read a book, touch an object, smell a flower, or hear music? Now, consider something as intricate as operating a car, for example. We need eyes to see the road, hands to control the steering wheel, and legs to manage the accelerator and brakes. All of those are vastly different types of, let's say, tools that perform completely different functions. Yet, they're all controlled by a single entity, the brain.
The master never touches the wheel, only pulls the strings that make it turn.
The brain itself never directly touches the steering wheel or sees the road, right? Instead, it operates through a sophisticated coordination system, the nervous system. When your brain decides, hey, turn left, it doesn't need to understand the mechanical details of how muscles contract or how joints rotate. It simply sends standardized electrical and chemical signals through the nervous system, and your hands know how to grip and rotate the wheel. Similarly, when light hits your retina or there, your eyes convert that information into the same type of neural signals that your brain can process, regardless of whether you're looking at a traffic light or reading a street sign. Now, here's where this gets interesting for AI systems. The large language model functions as the brain, making decisions and generating instructions that never directly interact with the outside world. An agent serves as the nervous system, coordinating between the brain's high-level intentions and the specific actions needed to accomplish them. Then we have Model Context Protocol, or MCP servers, that act like our specialized organs. Some might see by processing images, others might manipulate by controlling APIs, and still others might remember by accessing databases. Each MCP server performs completely different functions, yet the agent communicates with all of them through the same standardized interface. The beauty of MCP servers lies in their diversity and specialization. Just as our body has organs optimized for completely different tasks, each MCP server can be purpose-built for specific functions. One might connect to a weather service, another to a database, a third to a calendar system, and yet another one to the file system. Some might be simple tools that retrieve information, while others might be complex systems that can perform intricate operations, complicated operations. And here's what's really cool about this. No matter what each MCP server actually does behind the scenes, they all present the same interface to the agent. This standardization means that new capabilities can be added to the AI system simply by connecting new MCP servers, without requiring the agent or the brain to learn new communication protocols. Just as your brain doesn't need to learn separate protocols for controlling your eyes versus your hands, the AI brain doesn't need different methods for accessing a calendar versus sending an email. The agent translates brain's decisions into the appropriate commands and communicates with all MCP servers through the same standardized interface. Each MCP server responds through this unified protocol, creating an intelligent system where the agent can seamlessly coordinate between the brain's intentions and any tool or service in the digital world. Through this unified architecture, AI systems can accomplish the same complex, multifaceted tasks that humans perform daily by reading, manipulating, sensing, and responding to the world around them. And now comes the complicated part. Let's take a look at a few MCPs that you might be using, but you probably shouldn't. The results might change how you think about MCP architecture completely, entirely, partly. We'll see. We'll go through them from Cloud Code, but the same observations could be made in any coding agent, be it in a terminal or an IDE. Now, here's the thing. Let's start with a simple question like, hey, what's the status of the repo? We'll also add explicit use MCP instruction, mainly to ensure that this time it does use MCP instead of trying to do it without. We'll see without MCP later. The important note here is that the agent used git MCP to fetch the status of the repo and deduced that it is not a Git repository. Now let's fix that by instructing it to initialize it, create a GitHub repo, and let's push something. Everything. As one can imagine, it started doing just that. It used git MCP to initialize the repo and to add and commit files. Since git MCP is a reflection, a mirror of sorts of Git, it couldn't use that one to create a GitHub repo, so it switched to GitHub MCP. And then the moment came to add remote origin, but since Git MCP does not have a tool for that, it switched to Git CLI. The same happened with the push operation. That does not matter really for this conversation, and you should imagine that Git and GitHub MCPs can actually do all the operations they should be able to do. They're not, but imagine that they are. It should not matter that pushing with the CLI failed for reasons somehow related to the repo being created through the MCP. We'll ignore that as well. I want us to avoid complaining about the quality of those MCPs, as you will see soon, such complaints would be a waste of time. Instead, let's do one more operation with those MCPs by instructing the agent to delete the GitHub repo we just created. And there we go. GitHub MCP, remember, as expected, did exactly what we asked it to do. How about that? Wasn't that awesome, right? Amazing. We extended capabilities of the agent by letting it use Git and GitHub MCP, and as a result, the agent managed to do almost everything we needed it to do related to Git. Great, right? But wait.
Can you smell that? All of a sudden, the air around me started smelling like poop.
And I know what happened. When I said that we extended capabilities of the agent, a load of crap just exited my mouth. That's what happened. So, here's what I really discovered, understood, learned that completely changed my perspective. We did not extend anything with those MCPs. We did not enable it to do anything that it wasn't already capable of doing just as well, or maybe even better. And here's the proof. I'm going to exit Claude, remove Git directory we created earlier, as well as those two MCPs. Gone. Then I'm going to go back to Claude Code and send it the same instruction as before, but this time, instead of instructing it to use MCPs, I'll instruct it to use Git and GHCLIs. Just as before, it detected it is not a Git repo, so let's execute the second prompt. It initialized the repo, it created the GitHub repository, it added and committed files, and it pushed them. Everything worked just as before, except that this time, the agent did what needs to be done without using any MCP. If anything, this time, it did not fail to push to the repo. We can just as well repeat all the steps that we did with MCPs and instruct it to delete the GitHub repo, right? We can do that, and that worked. Why wouldn't it? We just saw why crap got out of my mouth when I said that we extended agent capabilities with MCPs. The agent was just as capable of working with Git without any of those MCPs. Adding them did not add any capabilities to it. None. And here's the thing. Models are already aware of the commonly used CLIs, and agents are capable of executing any commands from our terminals. In essence, the terminal itself is already the ultimate MCP. Think about it. To terminal access, agents can execute Git, kubectl, Docker, npm, Go, Python, and thousands of other commands. Each CLI tool provides its own protocol for interaction, and the agent already knows how to use them. All of them. I mean, not all CLIs, but most of them. Most of those that you are using. So, when we create an MCP that simply wraps Git status or kubectl get pods, we're essentially creating a slower and more complex version of something that already works perfectly. The agent doesn't need a Git MCP to call Git status. It can just call Git status directly through the terminal, which acts as MCP, and that is already available. This terminal as MCP paradigm is incredibly powerful because it means agents inherit the capabilities of every tool installed on the machine. Do you have, for example, GHCLI? Yeah. Well, your agent can manage GitHub repos. Do you have kubectl? Well, your agents can orchestrate Kubernetes. There is no need for additional MCPs for those cases. So, agent capabilities are actually limited to the machine where it's running. If you're working with Kubernetes, you almost certainly have kubectl, meaning that your agent can already use it to interact with the cluster. You do not, and I repeat, not need Kubernetes MCP if that MCP is a reflection of kubectl. And that part is important. If you're working with Go, agent is more than capable of building a project using Go CLI. So, you get the point, right? I hope so, at least. So, what's the takeaway here? First, don't waste your time adding MCPs that will enable your agent to do things it is already capable of doing, unless... At this point, you might think that I'm some kind of MCP hater, right? You might think that I do not believe they are useful. If that's what you think, you're wrong. What I'm about to show you will demonstrate the real power of MCPs. I believe that MCPs make our AI setup much better. I think that MCPs are what we need to make coding agents truly amazing. I also think that we should not design MCPs as mirrors of CLIs or APIs. They're bridges to capabilities agents might need and not, or shouldn't be, reflections of what we already have. Agents are trying to fulfill user intentions, and we should design MCPs to help them with that. MCPs should either provide access to tools and services that the agent cannot already access, or they should reflect user intents. The first group is simple. If, for example, we would like an agent to send a message to Slack, having an MCP that can act as a bridge between that agent and Slack makes a lot of sense. There is probably Slack CLI, but it's not widely adopted and models aren't familiar with it. There is an API that is frankly a nightmare. It's horrible, both for human and AI usage. Given all that, having a Slack MCP is an easy to recommend solution. The same can be said for many other services. Do you need to access Google Drive? Well, use MCP. Do you need to send email? MCP. You get the point, right? But here's where it gets really interesting. Beyond simple service access, there are MCPs with higher level tools, especially those that reflect user intentions. Let's take a look, for example, at AWS as an example to illustrate this concept. What one might need AWS for. Let's come up with an example. One way to describe what one might need would be to say, hey, we want to create and manage VPCs and subnets and internet gateways and node pools and other low-level resources. If that's what we need, agents are already perfectly capable using AWS CLI or applying Terraform modules or something similar. Most of the time, that's not what we want. Most of the time, we want something more specific. We might, for example, want an EKS cluster. That's why we create Terraform modules or cross-plane compositions. That's the purpose of them. Before AI, at least. However, for the sake of the argument that I see that I'm not making yet, let's say that we don't have any of those. Neither Terraform nor cross-plane or none of those tools. How can we use AI to create and manage an EKS cluster? Should we instruct an agent to create a VPC, a few subnets, an internet gateway, a node pool, and whatever else is needed to have an EKS cluster? Maybe. If we do, we can just let the agent use AWS CLI. That's all it needs. However, AWS created a special MCP server just for that. That over there is Amazon EKS MCP server. What makes it special is that it is focused on intents users might have. We can use it to manage EKS itself, resources inside an EKS cluster, applications inside it, to get logs and metrics from CloudWatch, and to deal with identity and access control. Now, I'm not saying that AWS EKS MCP is perfect. There's a lot, and I repeat, a lot over there left to be desired. A lot. But that's beside the point, though. What I'm saying is that it demonstrates the right approach. It is not a pure reflection of their API or their CLIs. It is focused on EKS. It combines different APIs into something meaningful like management of a cluster. It has potential. It can be useful since it does not perform exactly the same operations AWS CLI performs, but is focused, at least partly, on what we might need. Given that we transmit our needs to agents, it makes perfect sense that agents benefit from MCPs that have a similar focus. You tell the agent that you want an EKS cluster, and the agent finds out that there is an MCP tool that does just that. That's how it should be. To further illustrate this principle, let's switch to an example that is very, very dear to my heart. Very dear. Now, let's take a look at MCP servers. There should be only one, .ai. If we take a look at the tools, we can see that one of them is recommend. Now, before we proceed, let me explain what I wanted to accomplish with that tool. I want users to specify their intent, what they want, related to applications, and for that MCP tool to return a recommendation for how they should get such an application. If, for example, user says, hey, I want a backend application that is scalable and accessible from outside the cluster, then that MCP tool would provide a few combinations of Kubernetes resources that would accomplish just that. The simplified version of the process is, hey, discover which resource definitions are available in the cluster, instruct the agent to select a few combinations that would meet the user's intent, send schemas of all those resources to the agent so that it can construct resources for each of those combinations and come up with questions it might need to ask the user to clarify details. Then we execute dry run to validate that what it constructed actually works, and finally present the solution to the user. Easy. If that MCP, the one I created, would follow the logic many other MCP tools are following, there would be a tool that discovers which resource definitions are available. That would be equivalent to kubectl get CRDs. Then there would be another tool that retrieves schemas for each selected definition. That would be more or less the same as kubectl explain command. Then there would be a tool that executes dry run, which is essentially kubectl apply -- dry run. There would be no need for my MCP. Why would you need it? It could be done with the Kubernetes MCP or, as we already established, by the agent using kubectl directly. Would that agent know what is the process? Probably not. Would it work? Sometimes it would, often it wouldn't. Would generic MCPs that mimic CLIs and API help? Not at all. My MCP actually works, or that's the idea, it's in very early stages, because it is focused on user intents. A user can ask the agent something like, hey, I want to create an app that looks like this. The agent in turn knows that there is an MCP tool that can help. It knows what the intent is to create an app, and it knows that it can use that specific MCP for that specific intent. The agent has a specific task to perform that would be difficult to do using existing CLIs and existing knowledge in the model. That's a scenario where MCP helps. Okay, so now that we have a clearer idea what are and what are not good use cases for MCPs, let's discuss what should be inside those servers. And here's where most people get it completely wrong. Most people think of MCP servers as code that agents use to do something, right? The agent executes instructions from a model, and MCP provides a unified interface that the agent can use to do something or get some data. MCP is essentially a server like any other. It's data in, data out, like most other types of applications. Think of it like a backend app that exposes an HTTP API and talks to other apps, except that the API is now Model Context Protocol. That over there, what I just said, is certainly true for a significant percentage of MCP servers, but not for all. Now, here's where it gets really, really interesting. You can actually pack an agent into an MCP. That thing changes everything about how we think about MCP architecture. While there are specialist protocols for agent-to-agent communication, MCP has become the most widely adopted standard from the perspective of a client agent. It shouldn't matter whether an MCP server uses code or agents or both. It's simply yet another tool. So MCP servers can be typical code that does what code does, or it can be an agent that talks to a model. More importantly, it can be both. Some tasks are easier done with normal code, like the one code that we always had, while others are better done with agents talking to models. When deciding what goes where, consider this. Use code for operations that are deterministic and repeatable, like retrieving data from APIs or performing calculations, for example. Use agents for tasks that require interpretation or decision-making or working with ambiguous input. The most powerful approach combines both into a sequential flow. Code retrieves and structures data, agents process and make decisions, then code executes the results. Consider this simple example. A log analysis MCP. When a user asks, hey, are there any issues in my application logs? The MCP uses code to efficiently read and parse log files. A deterministic operation that's fast and reliable. Then it hands the structured log data to an agent that can interpret patterns, identify anomalies, and explain potential issues in human-readable terms. The code handles the heavy lifting of file I/O, while the agent provides the intelligent analysis. Makes sense, right? For a more complex example, consider the Kubernetes deployment recommendation tool from earlier. That's the one I'm working on, and I believe is a good example when combining both is a good idea. It, among other things, needs to retrieve all resource definitions from a cluster. There is no need to use an agent for that. No need. It's an operation that is always the same, and as such, it is faster and more reliable doing it as code. On the other hand, it also needs to pick which resources match user intent. That's where agents connected to models excel. There's parsing of an intent written in English, there's thinking evolved, and there's comparison with existing knowledge available in models. This hybrid approach offers several benefits: better performance for routine operations, intelligent handling of complex decisions, and cost optimization by using expensive model calls only when necessary. The trade-off is increased development complexity, but the capability gains usually justify the effort. With all that in mind, I suspect that we will see more and more MCP servers that partly use agents and partly execute typical backend code to retrieve data or perform some predefined workflows. But here's the key question. How do you actually structure this data flow? Regardless of whether an MCP server uses pure code or pure agents or a hybrid approach, they all share the same fundamental characteristics. They process requests and they return responses. Understanding this data flow is crucial for both using existing MCPs and designing new ones. When designing an MCP tool, the first thing we should think about is how will an agent know when to invoke it. The goal is not to say, hey, do this with that MCP tool, but instead just do this and let the agent figure out that this is best done with the specific MCP tool. That over there is actually trickier than it sounds. Unlike traditional programming where we code the exact workflows, MCPs provide only descriptions, and it's up to an agent, reinforced by a model, to figure out whether the description of an MCP tool looks like a good fit for what the user requested. Here's an example. By the way, I stored description input and output JSONs in files instead of making actual calls to MCPs. I'm doing that only to make it easier for you to see what's expected and what's happening. In the real world, those would be JSONs either sent to an MCP by an agent or responses from an MCP back to the agent. Capish? Okay, so the recommend tool, the one I'm working on, has a human-readable description that states that it can be used to deploy, create, run, or set up applications on Kubernetes. When that MCP is loaded, those descriptions are loaded into the context. From there on, if a user says something related to deployment, creation, running, or setup of an application, the agent will know that it should choose that specific MCP tool. We are not forcing the agent to do anything, but providing it with the information that a tool with specific capabilities is available to it if the need arises. From there on, it's all about the agent providing inputs to MCP and MCP responding with outputs. In case of that recommend tool, it knows what the input schema is. It should provide user intent as a string. Easy. As a result of all that, what the agent sends to that MCP tool would be similar to this example. This follows the JSON-RPC protocol structure where method specifies what action to take, params contains the parameters including the tool name and its arguments, and ID helps match responses to requests. The MCP server receives that and knows to redirect it to the recommend tool with requested intent. And once that tool is finished doing whatever it does, it responds back to the client agent with content. Here's an example. That's a simple one with type set to text and the whole response set inside the text field. Well, that text is perfectly readable by models. You might struggle with it, so here's a formatted version of that same response. That whole text is, in this case, arbitrary. It's whatever that MCP tool wants to send back to the agent, which, with the help of a model, will process whatever it receives, and in this case, it will see that there is next action that instructs it what to do next. There is also a guidance how to present the information to the user. And that over there is brilliant, since it doesn't insist on a predefined output format, but instead it assumes that the agent will process it and, just like a human would, understand what to do with it as long as instructions are provided. That over there, what you just saw, was the simplest and probably the most common input-output format of an MCP tool. But there are other patterns you need to know about. Quite a few others. So, while tools are about executing actions and getting responses, sometimes MCPs need to provide access to existing data or content rather than generating new responses. This is where resources come in. They're MCP's way of exposing files, databases, APIs, or any other data sources to client agents. Resources in MCP are all about data that servers can expose to clients and models. So let's say that we have an MCP that provides logs to the client agent, like Cursor or Cloud Code, the one that you're using directly. Here's an example of an input that an agent would send to an MCP server. That input requests application logs from a file log/app.log. The MCP tool could in turn respond with something like this. That output can be interpreted as, hey, you wanted logs from that file, here you go. It's in the text field. Now, another useful MCP protocol is related to prompts an agent might need. Let's say that we would like to have an MCP server that provides predefined prompts similar to Cloud Code/commands or cursor rules and so on and so forth. Now, you might be wondering, why would we want that? Why would we not use /commands or cursor rules? There can be many reasons. We might want to have prompts that work with any client agent, or we might want to generate prompts dynamically based on real-time data, or we might want to compose prompts based on internal workflows, or we might want them to be discoverable or parameterized or anything else. There are many, many reasons why having prompts in an MCP server is a good idea. So, how would that work? What's the flow here? 1. Client agent asks an MCP server to give it a list of available prompts. 2. MCP server responds back with a list which, for example, might contain a fetch PRDs, for example. Then, client agent asks the MCP for the fetch PRDs prompt, MCP gives it back to the client agent, and client agent executes it. That flow over there is essentially the same as the flow we would get with almost any other agent that supports custom prompts. In Cloud Code, for example, we would type /, which would list all available prompts. They call it /commands. We would select one we are interested in. Cloud Code would read it and send it to the agent, which would execute it. The major difference is that with the MCP acting as prompts database of sorts, that would work with any agent. I feel that's important since AI is a very, very fast-moving segment of the industry, and we are likely to change agents every once in a while. Even if we don't, one person in a company might use one agent, while the other might use a different one. Serving prompts through MCPs is an agnostic way to provide reusability. Here's an example. Let's say that I have this prompt. If I would like that prompt to be served by an MCP, it would send the following response back to the client agent. Look at it. It's easy. It works. It's great. It's better than assuming that everyone uses the same agent. If you already have prompts, wrap them into an MCP. It should not take more than, probably an hour of work from scratch. Now, let's switch to sampling. Sampling is great when you do not want to embed an agent inside an MCP or when you want user to maintain control through client agent. Let's say that your MCP needs to process something through an agent. Let's imagine that the recommend tool we discussed earlier, the one I'm developing, does not have an agent embedded. Such a variation of the MCP would still gather all the Kubernetes resource definitions and schemas, but when it comes to the agent assembling the solution that matches user intent, the flow would be different. It would be like this. MCP server sends sampling requests to the client, instructing it to construct Kubernetes resources for the application type previously specified by the user. Next, client agent reviews and potentially modifies the request. Then client agent talks to the model by passing it all the info it got from the MCP. Then client agent reviews the response from the model, and client agent returns result to the MCP server, which in turn does whatever else it is supposed to do. The sampling approach offers several advantages over embedding agents directly in MCP. To begin with, context preservation. The client agent maintains full, complete conversation context, which can be lost when passing control to an embedded agent, or even any other agent. Then we have user control. Users can review, modify, or reject the MCP's requests before they are executed. And finally, flexibility. Client agents can apply their own logic, constraints, or safety measures before processing MCP requests. There's one more though, actually. There is simplified MCP development. MCP servers can focus on their core functionality without managing agents' complexity. However, embedded agents also have their merits. There is performance. Direct model access eliminates round-trip communication overhead. Then there is autonomy. MCPs can make decisions and iterate without constant client interaction. Finally, there are specialized models. MCPs can use domain-specific models optimized for their tasks. The choice depends on your specific needs. Use sampling when you need user oversight, complex context management, or when the MCP's decision-making should be reviewable. And then use embedded agents when you need it to be fast, when you need autonomous processing, or when the MCP has specialized requirements that benefit from direct model access. Here's an example. Once such an output is received by the client agent, it would construct resources MCP requested with or without user being involved and respond back to the MCP with something similar to this. All in all, if your MCP needs client agent to do something, sampling is the way to go. Now, let's move to routes. Sometimes we might want to define boundaries to operations and resource access an MCP should have. For example, we might want to restrict it to work only within a specific directory or to communicate only with specific APIs. When we need something like that, we can use routes which are loaded when MCP connection is established. Routes serve as a security and organization mechanism. It is telling the MCP server exactly what it can and cannot access. Think of them as a whitelist of allowed resources. Here's an example. In this example, the MCP server can only access files within the backend service directory and the specific GitHub repository. Any attempt to access files outside those boundaries should be rejected by the MCP server. Maybe. This is probably the weakest story of MCP altogether. Slight problem, or maybe not slight, a big problem is that enforcement works through validation within the MCP server itself. When a client agent requests a file or resource, the MCP server checks if the requested URI falls within the defined routes. If it doesn't, the request is denied. And that means that MCP server developer is responsible for implementing those boundary checks. Routes do not automatically enforce themselves. The flow would be more or less like this. Client agent connects to the MCP server and declares that it supports routes capability. Then client agent sends initial routes to the MCP server during connection setup. Then MCP server stores those routes and validates all subsequent resource requests against them. When the agent requests a resource, the MCP server checks if the URI is within allowed routes before processing. Finally, requests outside the defined boundaries are rejected with an appropriate error message, assuming that you trust the developer of MCP. So beware with that feature on third-party MCPs. Nevertheless, this approach is particularly or somehow useful for corporate environments where you want to ensure MCP servers can only access approved code bases or APIs, and they're providing both security and clarity about what each MCP can touch. So there you have it. Most MCPs are indeed useless because they're just slower versions of tools that already work perfectly. The terminal itself is the ultimate MCP, but the 5% that matter, well, those are game changers. The key is focusing on user intent rather than mirroring CLIs. Build MCPs that provide access to services agents cannot reach. Or, even better, MCPs that understand what users actually want to accomplish. Then combine code for deterministic operations with agents for intelligent decision making. And remember, it's not about the tools, it's about the data flow patterns that make everything work together. So, what's your next step? Well, you should probably audit your current MCPs. Are they extending capabilities or just adding complexity? If they're not doing something fundamentally different from what the terminal already provides, it's time to simplify. Focus on the patterns that actually matter. Thank you for watching. See you in the next one. Cheers.